Okay, so welcome to the 13th video in the Discrete Structures series, and in this video we'll be covering the topic of primes. We'll look at the definition and explore a few details. Then we'll have a look at the Fundamental Theorem of Arithmetic, and this is a direct outcome of primes. Next we'll have a look at the concept of GCD or greatest common divisor. And we'll look at two terminologies that are an outcome of GCD, and they are the term relative prime and similarly pairwise relative primes. And then we'll look into the concept of the least common multiple, LCM, or least common multiple. And then we'll explore a few numeric problems. So these are pretty basic topics, but the next video is going to be about the Euclidean algorithm. And a few properties that we study in this video are going to be greatly relevant to the discussion of this. Okay, so that's the overview. Let's dive into our first topic. So talking about primes, I don't think anybody watching is unfamiliar with this concept. So prime is basically any number which can only be divided by 1 and itself. So basically 7 is a prime because the only factors of 7 are 7 and 1. And 12 is not a prime because it has factors like 4. So this is a very trivial concept, but you should know that primes form a building block of numbers, and we'll see that later in the Fundamental Theorem of Arithmetic. And so before I jump into that, I want to introduce you to a little trivia. So you must have heard the name of the mathematician Euler, and Euler came up with this expression, n squared plus n plus 41. Okay, and this is called a prime generator function. So let's say I plug a 1, I get 1 plus 1 plus 41, alright, it's 43. So this does not promise to generate all primes, but it promises that all the numbers that it generates are primes. But does it really? Well, it turns out that prime numbers are not so simple, and this fails after n reaches a certain point. So I invite you guys to do an internet research to see what value of n doesn't generate a prime anymore. Okay, so leaving this aside, let's come back to our fundamental theorem of arithmetic. Alright, so this states that every positive number, and that is greater than 1 can be expressed as a product of primes. Let me note that down, can be expressed as a product of primes. And you must remember doing this from your primary school. So taking a number like 48 and recursively dividing by the lowest prime that you can find. And so these would have been the factors. And it's easy to see this for a fact. So whatever number, right? So let's say n can either be a prime or it can be just not prime, right? So we call that composite. A number that is not prime is called composite. And if n is prime, my problem is already solved. You see, writing 3 as a 3 also counts as a product. If the number is already prime, it is already expressed as a product of primes. And if a number is composite, it's at least a product of 2 factors. And then I would ask the same question as I did with n. The factor 1 could be prime or composite, and so could be factor 2. So if I continue this tree, I eventually have to hit primes. Because every time I'm branching from a node, the resulting numbers are getting smaller because they are factors. So there is obviously also a formal proof to this, but that is out of scope for us. But this should give you an idea of why this is true. Okay, so for given any number like this one, you should be able to use this process to get a result like this. Just in case this is asked as an auxiliary question. Okay, so getting into our next topic, we'll be looking into the idea of GCD or greatest common divisor. And I cannot think of a better example of a name being the definition. So given any set of numbers, the GCD is the largest number that divides all of them. Okay, so if the GCD of A and B is, let's say, G, so G is the GCD of A and B, G divides A, G divides B, and G is the largest integer that does both of these. So for example, if I'm given 16 and 20, I can see that 2 divides both 16 and 20, but 2 is not the largest number that does it. The largest number is 4, and therefore the GCD of 16 and 20 is 4. So next we'll look at two terminologies that arrive from GCD, and the first one is relative prime. And getting straight to the definition, two integers a and b are said to be relatively prime if their GCD is 1. So let's take an example. So let's think of numbers 21 and 22. So none of these two numbers are primes, But the biggest factor that they share is 1. You wouldn't find a bigger number than 1 that can divide both 21 and 22. And that arises from the fact that 21 can be factorized as 3 times 7 and 22 can be factorized as 2 times 11. And if you see this set of factors, there's nothing in common. So the idea of pairing numbers that do not share factors is really useful. And this has applications under various encryption algorithms. And there is one more terminology, since here I'm taking only 2 numbers, but I can take any larger set of numbers and consider 2 numbers in pairs. So what does that mean? So let's say I have 3 numbers, 10, 17, and 21. And let me write the factors of these numbers for more context. These 2 are already primes. Okay. Now if I were to take every possible pair of these numbers, and if I were to discover that none of those pairs shared any common factors, I could conclude that these set of numbers are pairwise relatively prime. Okay. So to define this formally, a set of integers, let's say a1, a2, a3 all the way up to an are said to be pairwise relatively prime if and only if the GCD of every pair is 1, and I express that by writing this way. So the GCD of every ai, aj is gonna be 1, and I and j are gonna range for the entire series from 1 to n. And I could mention that fact by writing both I and j range between 1 and n. Okay, so next we'll have a look at the concept of least common multiple or LCM. And also from the name, the LCM is the smallest number that is a multiple of all the given numbers. So let's say I want an LCM of 4 and 5, then 20 would be the smallest number that is divisible both by 4 and by 5. So this is the least multiple common to all the numbers, 4 and 5 in my case. And we generally denote LCM AB as the LCM of numbers in here. Okay, now let's have a look at a problem that formalizes the concept of the prime factorization method that we looked at before to find the LCM and HCF of 2 numbers. So I'm going to put a question here. Use prime factorization to find the LCM of these numbers. Okay, so 12 and 18. And let us look at what we used to do as kids, and we'll see that we do the same thing now. So let me draw this border. So we used to say 12 equals, just factorize it. So 2, and that's 6 left for me. So I can take a 2 again, and that's 3 left, and that 3 would go here. And similarly, 18 could be written as 2, and that will leave me a 9, and 9 is 3 times 3. So we learned to circle these common factors. So 2 is common here, 3 is common here. And then we said that the GCD would just be the common numbers taken once, right? So in this case, it would be 2 times 3, and that would be 6. And then we would say the LCM, or the least common multiple, is common things taken once and everything else. So that would be 2 times 3. I took this 2 and this 3. And there is 2 and 3 again. So I need to take this 2 and this 3. And that would give me a 36. So we do this a little bit differently so that we don't look like kids, but it's essentially the same thing. So it's about writing in powers. So 12 equals 2 power 2 into 3. And similarly 18 is 2 times 3 squared. And then for the GCD, you consider the minimum power, while for the LCM, you consider the maximum powers. So what does that mean? See, so I could write GCD is equals, so I see a 2 here and a 3 here. And so the GCD would be 2 to the power of minimum of the powers, 2 and 1, as you'd see here is a power of 1, and so is here. And then I multiply this with 3 to the power of minimum of all the powers of 3, 3 and 1. Okay, so this would be 2 to the power 1 into 3 to the power 1. And that would give me the 6. And taking the least power ensures only the common groups are included. Because see, I have 2 3s here, but I only want 1 3 to be included. So I'm going to take the least of 2 and 1, which is a 1. And similarly, in order to get the LCM, you'd just be taking the maximum of these powers. So I think you can do that yourself. And I think there's one more thing to be careful about. So let's say it didn't ask you for 12 and 18, but rather 60 and 18. And the point I want to make is 60 would be factorized this way, 2 square into 3 to the power 1, that is the same, and I want to introduce a 5, this was my intention. And then 18 would be the same. This would be 2 to the power 1 into 3 squared. And since there's no 5 here, I want you to write a 5 to the power 0 here. Because you need this 0 to compare against a 1, okay? And when you're taking a minimum, this 0 would be selected over a 1. And that is why factors that appear in only one number does not go into the GCD. Okay, so this one doesn't go into the GCD because it has no corresponding pair in the other set of factors. So always ensure that you have exactly the same prime numbers 1 to 1, and you introduce the missing ones with the power of 0, and then you can proceed into the minimum and maximum process that we did here. Okay, so that should conclude the contents of this video. This was pretty basic, I'll admit, but the next video is going to be about the Euclidean algorithm, and all of these things are a requisite to understand it. So that is it for this one. I'll see you guys in the next one. Have a good day. Bye.